Hey there, this is the lecture video for Chapter 5, Section 5. You made it to the last section of Chapter 5. Great job. We're going to be using some previous formulas again today, namely the mean, variance, and standard deviation formulas. So look through your notes and have those handy and look them over before we get started. Also, refamiliarize yourself with the calculator function that goes with normal distributions, normal CDF, because you'll be using that quite a bit and I'll expect you to know how to do it. There won't be a tutorial page on it in this video, so make sure you know how it works. Again, that was the normal CDF function. Okay, we're going to be doing a lot of work with z-scores, so if you like working with the standard normal table more than the calculator, or if you just think it helps as we go along, make sure you have that out before we get started. Okay, I think that's it. Let's get going. Welcome to the lecture video for Chapter 5, Section 5. Normal approximations to binomial distributions. In this section, we're going to learn how to determine when the binomial distribution can be approximated by the normal curve, how to find corrections for continuity, and then how to use normal distributions to approximate binomial probabilities. We'll start with a review of what we know about binomial probability experiments. We know that they must have only two outcomes, a success or a failure. We know that P and Q are fixed and they're independent trials. We also know that the random variable x counted the number of successful trials and that x could only take on non-negative integer values. And we use this fun probability formula to solve them. P of x equals n choose x times p to the power of x times q to the power of n minus x. And then we could use the calculator function binom_pdf to solve it, where we use the variables of n, or sample size, and p, or success rate, and x. An example of when we might use this formula would be a problem like this. A surgical procedure has an 85% chance of success. Out of 10 patients, find the probability of exactly 2 successful surgeries. We would fill in the formula with all the proper variables like so. P of x equals 2 equals 10 choose 2 times 0.85 squared times 0.15 to the 10 minus 2 equals 0.0000833326. Now, this formula is convenient for a small number of successes, or even if we had to find something like small stacked questions, such as less than 3 surgeries were successful, where you'd have to find the probabilities of 0, 1, and 2 successful surgeries. But it wouldn't work for the following as easily. You have 150 patients, and you want to find the probability of there being fewer than 100 successful surgeries. The problem is we'd have to do this formula for all iterations of successes from 0 to 99 in order to account for everything fewer than 100, and that would be a daunting amount of work. So we have a different way of going about this. What if I told you we can use a normal distribution to approximate a binomial distribution when it's impractical to use the binomial distribution to find a probability? You'd probably say, duh, isn't that the name of this section? Of course, you'd be right, but I'm trying to get you to suspend your disbelief here. Okay, so yes, you can use a normal distribution to approximate a binomial distribution that has a high number of trials. I'm going to show you why we can do this. We're going to use the test situation of a binomial distribution that has a p-value of 0.25 or 25% chance of happening, and a q of 0.75. Then we're going to play with the sample size. I want you to see what happens to the shape of the graph as the sample size grows. Here's the graph at sample size n equals 4. It's clearly a binomial distribution with distinct bars, and you can see it's skewed to the right. What do you think is going to happen in n equals 10? Well, let's see. Interesting. So still discrete numbers and bars, still skewed right, but they're smaller and almost bunched together more. What about n equals 25? Let's look. Wow, this is different. The right skewedness has almost disappeared, and it has seemed to even out more. The bars have gotten thinner and more bunched together, and I don't know about you, but I would swear that graph is looking closer to a normal curve. Doesn't it look symmetric and bell-shaped? Let's try the next one, n equals 50. Okay, this one definitely looks more like a normal curve. Symmetric, bell-shaped, and the bars are very close together and thin. I might even theorize that the larger my sample size, the smaller and less noticeable my bars become, making them look more and more like a curve, a normal curve. Now, before you start thinking we can use this idea for everything, of course there are some conditions. Here's how we determine whether or not we can use the normal curve to approximate a binomial distribution. We need to perform a couple of products before we begin other calculations. We need to multiply n, our sample size, by p, our probability of success, and determine if that is greater or equal to 5. And we have to multiply our sample size by q, our probability of failure, and determine if that is greater than or equal to 5. If they're both greater than or equal to 5, then we can proceed. The way that a normal distribution approximates a binomial distribution is by affecting the following two formulas. These formulas then affect the standard formula, read z-scores, that you use to find probability. So first it tells us that it's changing mu to be sample size times probability of success. Well, you already found that in your test to determine if you could use normal distribution, so that'll be easy. Then it changes the standard deviation to be the square root of this product. Sample size and p and q, where q is the probability of failure in a single trial. Let's do a few examples of just finding the mean and standard deviation to get a feel for how this works. Two binomial experiments are listed. Determine whether you can use the normal distribution to approximate the distribution of x. The number of people who reply yes. If you can, find the mean and standard deviation. If you can't, explain why. In a survey of high schools in a certain state, it was reported that 40% of students failed at least one class taken through distance learning. You randomly select 45 students from that state and ask whether they failed at least one class through distance learning. Okay, we're going to skip over 2 for now. In this binomial experiment, n equals 45, p equals 0.4, and q equals 0.6. So we first need to do our simple products. We need to multiply n by p and n by q. When we multiply 45 by 0.4, we get 18. When we multiply 45 by 0.6, we get 27. Because NP and NQ are greater than 5, we can use a normal distribution to approximate the binomial distribution. So mu equals n times p, which we already found to be 18, and sigma, or standard deviation, is a square root of n times p times q, or 45 times 0.4 times 0.6, which is about 3.29. When we graph it, it looks something like this. The binomial distribution is approximately bell-shaped, which supports our conclusion that we can use the normal distribution to approximate the distribution of x. Okay, now back to number 2. In a survey of high schools in a certain state, it was reported that 18% of seniors were off track to graduate because of at least one course failure. You randomly select 20 seniors from that state and ask them whether they are off track to graduate because of at least one course failure. In this binomial experiment, n equals 20, p equals 0.18, and q equals 0.82. So we perform our products of n times p and n times q. For the first one, we get 3.6, and the second, we get 16.4. Okay, we have a problem here. Because n times p is less than 5, we can't use the normal distribution to approximate the distribution of x, and the graph supports this conclusion. A binomial distribution is discrete and can be represented by a probability bar graph, where the x values are non-negative integers 0, 1, 2, 3, and so on. To calculate binomial probabilities, the binomial formula is used for each value of x, and the results are added. A few sections ago, we talked about the area of a bar being similar to the area under a curve. We talked about how that would mean the width would be 1 and the length would be the probability or the height of the bar. Geometrically, this corresponds to adding the areas of the bars in the probability bar graph. Well, now we're going to actually work with that idea even further. Imagine a binomial bar graph. Its bars don't touch because it's not continuous. Now imagine we move half a unit to the left and the right of the midpoint of each x value. This would join each of the bars together and would effectively capture all possible x values in the interval. It would then act as a continuous graph would. Doing this, capturing half, or 0.5 of a unit on either side of a midpoint like this for a binomial distribution, is called continuity correction. So how do we do this? Well, it's actually just a matter of subtracting 0.5 from the bottom number and adding 0.5 to the higher number, depending on what the context. Now you need to pay attention to the situation. Sometimes it's going to ask you for all values less than something. That's going to require a different sort of answer than the numbers in between two values. So let's try a few and see where we are. First one, Use a continuity correction to convert each binomial interval to a normal distribution interval. Number 1. The probability of getting between 270 and 310 successes inclusive. Now this one is wanting between two numbers. So in order to make sure we're including both the lower and the upper number, we need to leave some space on the outside at either end. How do we do that? Well, we just talked about subtracting 0.5 from the lower end, so 269.5 and adding 0.5 to the upper end, or 310.5, would make sense. So the corresponding midpoints are all of the points in between, including the two endpoints. So 270, 271, etc., all the way to 310, inclusive. The corresponding interval for the continuous normal distribution is 269.5 to 310.5. Let's do another. Number 2, the probability of getting at least 158 successes. So this one we want at least some number, which means we want this number to be included, then all numbers above it to be included. The way to make sure this number is included is to subtract the 0.5 from the number, so you're leaving some room below it, and saying that x is any number larger than that resulting number. So the midpoint values are from 158 on, but 158 is the one we need to adjust, so 157.5, and our probability is the probability of x being larger than 157.5. Do you see how these are working? Let's do another one. Number 3, the probability of getting fewer than 63 successes. This time we're approaching it from the other direction. We want all the values less than 63. So the midpoints are all the numbers below 63, but notice the wording. It's not including 63. It says fewer than 63. So we're not including 63 in our list. So 62 is the last midpoint we're considering. So that's the one that we manipulate. The corresponding interval for the continuous normal distribution is x is less than 62.5. The normal distribution probability is the probability of x less than 62.5. Let's look at all the different ways these problems could be worded and what you need to do for each. If the problem says something about being exactly a value c, then you want to form a cushion of space around it on both sides. So you'll subtract 0.5 from it for the lower end and add 0.5 to it for the upper end. So your result will definitely include the named number. If the problem says at most c, it's including c and everything below c, but you want to make sure to allow for including c. So there needs to be some cushion at the upper end to make sure c is part of the included numbers. So you add 0.5 to the number, so it's definitely within the range. If the problem says fewer than c, this time it's not including c because it's saying fewer than c, not including c in the range. For this one, you decrease by 0.5 so that you're effectively including the number below, but not including c. If the problem says at least c, it is including c and every number above it. So you want to make sure c is included in the range, so you subtract 0.5 to make sure it's included. If the problem says more than c, it is not including c. So you add 0.5 to effectively include the number above, but not including c. Okay, so now that we know how to read it and how to use continuity correction, let's go through the steps of using normal distribution to approximate a binomial distribution, both in words and in symbols. Your first question you should ask yourself is if the given situation is a binomial experiment. Can you specify the values of n, p, and q? And can you determine that the outcomes are strictly successes and failures, and the trials are independent? Is the probability of success the same for every trial? If you're able to verify that it is a binomial experiment, then you can move to the next step. Now you need to solve those two products to make sure the binomial distribution is eligible to be approximated normally. Is n times p greater than or equal to 5? Is n times q greater than or equal to 5? If it satisfies both of those, you move on to the next step. Next, you find the mean and the standard deviation using the appropriate mean and standard deviation formulas for this situation. Mu equals n times p, and sigma equals the square root of n times p times q. After that, you need to apply the appropriate continuity correction. This will depend on the situation, which you need to determine based on context. You will either be subtracting or adding 0.5 to the given number or some number adjacent to it. Next, you will find the corresponding z-score. And remember, because the formulas for mean and standard deviation are different for this situation, you need to use them correctly because of the context. Be careful when you're plugging in that you're not blindly plugging in numbers. Finally, you find the probability using the standard normal table or using your calculator. Let's look at a few examples. 62% of adults in the U.S. have an HGTV in their home. You randomly select 45 adults in the U.S. and ask if they have an HGTV in their home. What is the probability that fewer than 20 of them respond yes? So what do we do first? Is this a binomial experiment? Are the outcomes successes or failures? Yes, either you have an HGTV or you don't. Can we determine the probability of success and failure? Yes, they have told us that 62% or 0.62 is the probability of success, or P, which in this instance means having an HGTV. So our P would be 0.62 and our Q would be 0.38. The trials would be independent because whether or not a family has an HGTV does not affect whether or not another family has one. Do we know how many trials or the sample size N? Yes, they told us 45 adults, so it is a binomial experiment. Next, we need to determine if this binomial distribution is eligible for normal approximation. To do that, we multiply N times P and N times Q. We get 45 times 0.62, which is 27.9, and 45 times 0.38, which is 17.1, both of which are larger than 5, so it is eligible for normal approximation. Now we find mu and sigma. We already found the value for mu, N times P, which was 27.9. Sigma is the square root of N times P times Q, which turns out to be about 3.26. Next, we have to think a little bit because we have to figure out how to apply the continuity correction. The question asked about fewer than 20. So 20 is not included, and we're wanting to know about numbers less than 20. So we need to subtract 0.5 from 20, which will effectively include the next number less than 20, 19, but not 20. So 19.5, or x is less than or equal to 19.5. The figure shows a normal curve with mu of 27.9 and standard deviation of about 3.26, and the shaded area to the left of 19.5. We already did the calculations for mu and standard deviation, so we can use those values now in our standard formula to find the z-score. 19.5 minus 27.9 divided by 3.26 is about negative 2.58. So the probability we're looking for is the probability of z being less than or equal to negative 2.58. You can use the standard normal table or the normal CDF function on your calculator using a large negative number as your lower bound to figure this out. You should get about 0.0049. So there is a 0.0049 probability, or a 0.49% chance, that fewer than 20 respond yes, they have an HGTV. Not too bad. Okay, let's do another. A study on aggressive driving found that 52% of drivers who use both alcohol and marijuana admit to driving aggressively. You randomly select 200 U.S. drivers who use both alcohol and marijuana and ask them whether they admit to driving aggressively. What is the probability that at least 100 drivers will say yes, they admit to driving aggressively? Okay, so first we need to verify that it is a binomial experiment. Yes, the subjects either say yes or no. Aggressive driving is equal to success in this experiment, and they gave us a 52% chance of success. So P equals 0.52 and Q equals 0.48. Our sample size N is 200, and since the fact that I answer yes does not affect whether you say yes, the trials are independent. Our next step is to see if it's eligible to be normally approximated. Well, N times P is 200 times 0.52, which is 104, and N times Q, or 200 times 0.48, is 96, so both are greater than 5. So it is eligible, and the binomial variable x is approximately normally distributed. Then we calculate mu and sigma with our formulas. mu equals 104, and sigma equals 200 times 0.52 times 0.48, which is about 7.07. Then we look at the continuity correction and see how it needs to be applied in this situation. The question says, what is the probability that at least 100 drivers will say yes? So we do want to include 100, and we want all numbers greater than 100. So we need to subtract 0.5 from 100 to make sure we have cushion below it, so it is included in the range of numbers. So we need to have the probability of x greater than or equal to 99.5. So we have a figure with the mu at 104 with a standard deviation of about 7.07 and the shaded area to the right of 99.5. The z-score that corresponds to 99.5 is figured out for you here, and it is negative 0.64. So because this is to the right, we either need to find our value on the standard normal table and subtract it from 1, or we need to make sure we know how to put our z-score as our lower bound and put a large number in our upper bound if we're using the normal CDF function on our calculator. When we do either of these, we find that the probability that at least 100 drivers will say yes is about 0.7389, or about 73.9%. Okay, one more just so we know how to do all types of these. A study of National Football League, or NFL, retirees found that 12.3% have undergone knee joint replacement surgery. You randomly select 100 former NFL players and ask them whether they have undergone knee joint replacement surgery. What is the probability that exactly 15 will say yes? Test for binomial first. Success and failure? Yes. They either say yes or no. Probability of success? Yes. They gave us 0.123 for success, or P, so 0.877 for failure, or Q. Whether one person has had knee surgery does not affect whether another has, so they are independent trials. Now we get into the binomial distribution and whether it's appropriate to be approximated normally. N times P is 100 times 0.123, which is 12.3. And N times Q is 100 times 0.877, which is 87.7. So the binomial variable x is approximately normally distributed because both of those are larger than 5. Next we figure out mu and sigma. Mu is already done, 12.3. Sigma is the square root of 100 times 0.123 times 0.877, which turns out to be about 10.787. Now we determine how to use the continuity correction. Well, in this case, they want to know if an answer is exactly some number. So the way we do it for this type of question is to give a cushion on both sides. So we'll subtract 0.5 from that number on the left and add 0.5 to it on the right. So we can rewrite the discrete probability of x equals 15 as the continuous probability of x from 14.5 to 15.5. The figure shows a normal curve with mu of 12.3 with a standard deviation of 10.8 and the shaded area under the curve between 14.5 and 15.5. If we figure out both z-scores, the value for 14.5 is about 0.67, and the z-score that corresponds to 15.5 is about 0.97. So we can figure this out by finding both z-scores on the standard normal table and subtracting one from the other, or we can use the normal CDF function on the calculator and have the lower z-score as the lower bound and the higher number as the upper bound. Either way, we find that the probability that exactly 15 NFL retirees will say that they have had knee surgery is approximately 0.0854, or about 8.5%. And that concludes our video for Section 5 and for Chapter 5. Good luck on your Chapter 5 quiz. I'll see you on the next video.